Thank you. Thank you very much and good morning. Today I will present evaluation of global climate datasets over Armenia. First, I would like to mention that I present Hydrometeorology and Monitoring Center, and we collaborate with the Institute of Informatics and Automatic Problems for a long time, more than 10 years. In our practice, we need powerful computing resources to run weather models, numerical weather prediction models, and climate models. Why these models are important for us and also for the entire globe? So climate models are used to assess climate change and to monitor the main components of the Earth's system. But today we will focus mostly on climate. I will start my presentation, and here you see the topographic map of Armenia. You see that Armenia is a mountain country. And also I present here the meteorological stations. We have 45, currently we have 45 meteorological stations operating in Armenia. Those stations are marked by green triangles on the map. And also you see some of the grid points, the location of the model data. We used two models. First is Sierra 5 land, which is the mixture of observations and model, and we call it reanalysis dataset. It has all main climate variables like temperature, precipitation, wind, and so on. And this model is higher resolution. It has a 10-kilometer global data sets, every 10 kilometers especially. And you see the black dots, the grid of the Sierra 5 reanalysis data sets covering Armenia. And the other climate data set is CSIT2023, which is used for climate prediction for 100 years later, let's say. But this model is coarse. It has a 100-kilometer spatial resolution. And you see the only 5 bold crests, they cover Armenia. So today we will evaluate the performance of these two different data sets against our observations. And here you see the graphs, the plots of comparison. First, I presented the annual cycle of precipitation, temperature and precipitation. You see every month, monthly temperatures for average for 30-year period. And the columns are observations from our meteorological stations. And the red line is the Sierra 5 land reanalysis, which has a higher spatial resolution, and the red line is from the climate model. And of course, you see that this Sierra 5 reanalysis performs much better, and the biases, especially in the summer months, is reduced. It's closer to our observations compared to the coarser resolution CSIT2023 model. And this is expected, of course, because Sierra 5 also using the different kind of observations, not only numerical weather, numerical climate model. And the same results for the monthly precipitation. Here we see that the bias in simulating precipitation is reduced in the CSIT2023 model, but Sierra 5 data set is over-predicting or overestimating the monthly precipitation in Armenia. So we have a peak period in the spring months, in the May, and the lowest precipitation in this month, in September, according to our observations. And the right side plot, they present some statistical scores, like RMSE, root mean square error, bias, and also correlation coefficient. Here we evaluated only CSIT2023 model. And I would say that the errors are quite high for the global model, and this means that we need to improve and use higher resolution and better model for Armenia. So we have from 2 to 4 degree error, but the highest errors are for winter and summer season. So in summer season, which is the hottest season in Armenia, we have higher errors and we have strong overestimation of mean temperatures in the model. And also, this is for temperature, and also for correlation coefficients, we have quite low correlation coefficient, slightly exceeding the 0.3. And this is more or less the same for all season, and the worst season is the winter. So model has some challenges, difficulties to accurately represent the winter season temperature. Okay. So here we present the dynamical time series of temperatures starting from 1961 to 2005. This covers the historical simulations from these models. So the red is observations, and we can see the CSIT model in black and verified in the yellow lines. Again, when we compare the two global data sets, the Europe one much better represent the annual anomalies in temperatures over Armenia compared to the observations, while the errors in the CSIT model higher. And when we compare the temperature trends, you see that the model overestimates temperature increase over Armenia. According to observations, you see the coefficient of slope. It's only 0.2 degrees per decade, per 10 years, but the model shows 2 times faster increase of temperature over Armenia. And this is the same comparison, but for precipitation. And again, we see that the Europe land reanalysis data set is really much better with observed data compared to the CSIT model. So we use these climate models to project temperature change in Armenia in future, let's say up to the end of the 21st century. We present the observed mean temperature for this historical period, 30-year period, and the projections or prediction of temperature in the end of century in the let's say under the two scenarios. The middle one is the middle scenario, and the right one is the worst scenario. These scenarios are based on the emission of CO2 from fossils and from the human activity, and there are different projections. So you see clearly the temperature increase predicted by CSIT model, and the blue ones show the negative temperatures, temperatures. You see that the blue colors are disappearing in future, even over the high mountain areas, and I think Arabic mountain. So this is concerning for snow, for water resources, and for everything in Armenia. Okay, now I want to demonstrate you one case study when we observed very severe drought in Armenia. It was in 2021 in June. This month was the warmest, or let's say hottest, and the driest month in the history of observations since 1935. And I want to say that one of the most clear signal of climate change is temperature increase in summer, which leads to higher frequency of droughts, heat waves, and now let's analyze this case study. So you see the map of temperature anomalies from all meteorological stations and from the Europe global data sets, and they agree. And you see that the temperature anomalies were quite high, like 3-4 degrees above the norm. And we have over entire Armenia and over entire South region. And the same from precipitation, the temperature of precipitation was very low. You see that only 10 to 20% of precipitation observed in this month, and Armenia and the entire region were very dry. Additionally, we can put it so-called drought indices. They are used to assess the intensity of droughts. So these are the international drought indices recommended by World Meteorological Organization. The upper row, you see the categories of the droughts, and the red colors show the severe and extremely severe droughts categories for Armenia. These are computed using our meteorological station observations. It includes precipitation data, maximum temperatures, and wind. And mostly our drought indices, they agree, showing severe and extremely severe droughts in June 2021. And also we use dynamic hydrothermal coefficient for 10-day periods, and they also show that especially Yerevan, Central Armenia, and Southeastern Armenia, they are affected by severe droughts, and there are also some significant economic consequences because of this severe drought period. And this is from satellite observations, because vegetation indices are widely used for assessing droughts. And this is from MODIS satellite, which has around 200 meters spatial resolution. And we can assess how these severe droughts affected our vegetation. And again, the red colors show that vegetation were negatively impacted by severe drought in Armenia. And so this allows us to compare our meteorological assessment, from our observation of temperature and precipitation, and this link to the vegetation state from satellite observations. And here I would like to mention that we, this year, in the beginning of this year, we developed community practice, which is a platform, virtual platform of drought management in Armenia. And this is supported by Visegrad Fund from the Eastern Europe. And together with the Hydromet Service of Armenia, we created this virtual platform, and we issue monthly bulletins of drought. So everyone can, if interested, can download this information. And this is also important and useful for users and for farmers, because again, the drought are the main issues under current climate change in Armenia that we face now. This is all from my side, and thank you very much. And if you have any questions, I'm happy to answer. Thank you.
I'm a researcher from Institute for Informatics and Automation Problems. It's a great pleasure for me to present my research work entitled Enhancing Earth Observation Data Processing through Optimized Multimodular Service, which is within the framework of Swiss-Armenian joint efforts to handle EO data processing challenges. The outline of my presentation is the following. At the beginning, I will speak about the challenges of EO data, then focus on our goal and suggested solutions. To show the effectiveness of our solution, I will bring some experimental evaluations, which will be finalized in the conclusion. Earth observation, or EO data, refers to the collection of information about the Earth's surface, atmosphere, and oceans using remote sensing technologies. It's worth to mention that EO data is widely used for solving many scientific and societal problems, such as urban planning, weather forecasting, environmental monitoring, climate changes, etc. One of the largest EO data provider is Copernicus, which provides data from several open source satellites, such as Landsat, Sentinel, MODIS, and each daily generates 250 terabytes of data, and the full archive size is approximately 250 petabytes of data in Copernicus. So the characteristic of EO data creates challenges such as volume, complexity, and variety. Volume, managing, storing, and processing of such large-scale EO datasets, it's hard challenge and requires intensive resources and complex solutions. Complexity, EO data is complex as it comes with different resolutions, including spatial and temporal resolutions. And variety, EO data comes from various satellites, which has different kinds of sensors and gadgets. So in order to handle EO data efficiently, we need to consider both processing and storage layers. Due to the three-dimensional nature of EO data, where the dimensions are time, latitude, and longitude, this EO data can be easily, the processing of this data can be easily parallelized. So EO communities widely use high-performance computing and cloud infrastructure in order to do distributed computing of EO data and to achieve fast data processing. However, here the question is which kind of cluster to select, how many nodes to have, and the characteristic of these nodes in order to achieve optimal objectives such as performance or cost. In the storage layer, EO data formats provide data compression methods. Each compression has different compression vector. So a high compression vector will reduce the size of data and therefore reduce the network transfer time. However, it will require more time to decompress this data during the processing. In the scenario for the weak compression is the opposite. So finding the trade-off and therefore the optimal data compression method for handling EO data is challenging. Making informed decision regarding to data compression and cluster configuration setup for storage and processing layers is essential. So the goal of this research is to develop an optimized multimodular service for EO data management in response to these challenges. The architecture of the suggested multimodular service is presented in this slide. So client can access to this service using REST API. Service provides the following optimization solutions. It provides data compression recommendation, execution time and resource cost estimation, optimal cluster configuration suggestion, and finally, scalable and distributed data processing. This service consists of several modules. So the core module here is Manager, which communicates with other modules and provides the optimized solutions. Here, decision-making module provides improved and optimized solution based on pre-trained regression models and simulator. Scalable processing module provides distributed processing of EO data using task parallel Python library and Kubernetes. And finally, data repositories module provide EO data. Here we use two kind of repositories, local and global. As local repository, we use Armenian data group, which provides data of the territory of Armenia. And we also use some global EO data repositories, for instance, Sentinel-2 cloud optimized IoTs. To show the effectiveness of the platform, we calculate normalized difference vegetation index, or NDVI, which provides the health of the vegetation. So we calculate average NDVI for Armenian territory, considering input data compressed with different compression methods, which are supported for EO data. And also we did simulation considering different cluster configurations. So in this slide, you may see execution times with various data sizes and compression methods. X-axis here is data size, Y-axis execution time, and with the color you can differ the data compression methods. In this slide, it's worth to mention that this standard data compression method provides approximately 5 times faster execution time than template, which was selected as default by global cloud by global repositories. Also, to show the effectiveness of estimation module, here you can see the comparison of execution times of actual execution time compared with the estimated ones. In this figure, x-axis is number of nodes in the cluster, y is execution time. In color, you can see the instance types. For instance, the blue one corresponds to the nodes which have 2 cores and 4 GB of RAM. And here we have two kind of shapes as points, square and circular. Square points correspond to estimated execution time, while the circular ones are real. And the comparison shows good accuracy between these two execution times. Correspondingly, R square was equal to 0.88 and root mean square error to 78. And optimal cluster selection is done by using Pareto multi-objective optimization algorithm. Here we use two kind of objectives, execution time and cost of the resources. If you are using some global cloud resources of global cloud providers, you need to pay for it. So here objectives are depicted in axis, and each point here corresponds to one single cluster configuration. And here we have 3 optimal cluster configuration, which are shown in red color, while the blue ones are not optimal. And in the shaded area shows the dominated area by this red point. And the blue points, which are in this shaded area, provide more execution time and more cost than this red one. So concluding my presentation, this research work proposed a multi-modular service which provides optimal configuration selection for efficiently handling EO data at both storage and processing layers. According to the evaluation, selecting the optimal data compression method may improve the efficiency of distributed computing, and the optimal cluster configuration are evaluated and selected using Pareto multi-objective optimization technique by considering two objectives, performance and cost. This research was supported by Science Committee of Republic of Armenia and the University of Geneva. Thank you. That's all. Thank you, bro. Hello, I'm Victor from Crest Group in Adelaide University in South Australia, and I'll be talking about energy efficiency evaluation that we did with several data storage solutions. So firstly, to introduce the concept of cyber foraging, as it's known, where we try to utilize our resources more efficiently. We borrow them from where we have and use them where we don't have them. For example, we can apply this to CPU or storage. Typical mobile phones could offload the photos we take to the cloud because we don't have enough space in the phone itself, but the cloud resources are considered to be unlimited. When trying to share remote resources, we have to have a few considerations. For example, the latency, because it will take time to upload the data and receive it back. We have privacy considerations because sometimes we don't want to share sensitive data. And lastly, the focus of this work is the energy consideration, because when we send the data, wait for the processing to complete and receive the data back, this all still consumes the energy. And we can still maybe do the same task locally rather than offloading and compare and see which one consumes less energy. In this study, we looked in 4 popular data storage solutions. MongoDB, which is JSON-like document-oriented database, Redis, which is in-memory key-value storage, Cassandra, white column store, and more traditional, well-known MySQL relational database. For the evaluation, we used the popular YCSB benchmarking tool. It's a very popular solution, which is Java-based, and it's very extensible. It supports over 40 different types of databases, and people still develop new plugins to support more. And it's very flexible in terms of which workloads we apply. We can define multiple parameters to simulate any workload we like. So that includes number of records we want to process, or number of operations we want to do, the distribution of data, for example, it could be random or more specific. Then, of course, the record size, contents. It also has a few dozens of parameters, for example, with duration of the execution and so on. But here we mostly relied on the default one because YCSB provides what they call a set of core workloads, which are very typical and met in industry very commonly. For example, and they label them with letters from A to F. For example, workload A is update heavy workload, which is 50% reads and 50% write. Workload B is read mostly, which is 95 read and 5 write. And the others are read only, read latest, short ranges, and read modify write. Out of those, the most interesting is the workload E, because it operates on ranges of records rather than individual records. And each of those workloads is typical in certain situations. For example, when we do online shopping, people perform more reads because they keep scrolling through products and they buy once in a while, not very frequently. For example, short ranges is used to select ranges of records. Typical example they provide is forums. When we click a particular topic, we want to see all the records associated with that particular forum topic only. Also, we had to consider the order of the workload of the execution, because some of those, notably workload D, changes the number of records in the database. So if we want to keep things fair, what we do is we load the data first, perform all those workloads which do not change number of records. Then we do lastly the workload D, which does, and then we flush the database contents and load again this generated data, so we can conclude with workload F here.
What we try to do here is we measure energy usage on the client side because we assume that the cloud or the remote node is connected to the power and has no problems with energy. But we are more concerned that on the client side, it would be a mobile or restricted device which is on a battery. And this is why we are concerned about having low energy expenditure. For this, we use the RAPL technology, which is developed by Intel. It is a software model, but because they have very good knowledge of the CPUs they develop, it's quite precise, and they have proven that comparing actual measurements with their model, it's very precise. And what it does, it provides the readings of how much CPU consumes in joule. So for this experiment set, we tried to use different types of nodes. So what we call a mid-range CPU is a regular laptop. What we call a more powerful node that would process remotely, and one virtualized node in our local cloud infrastructure. So this provides the overview of the CPUs used in all those three nodes. And when we wanted to test the actual expenditure of the energy, we tried to look into different scenarios. For example, in first two scenarios, we try to conduct the same operations locally, which means the YCSB and database itself were installed on the same node, and the same operations were conducted without any offloading. This would serve as a baseline for us. And then we tried to do 3 offloading scenarios, 2 in close proximity. Those were conducted within Adelaide University. And long-range offloading was conducted within the city limit. So the close proximity was between 2 buildings was 1.2 milliseconds, and the long distance offloading was around 50 milliseconds within the city limits. So the offloading scenarios we did was from mid-range CPU to high-end, from high-end to OpenStack, and from mid-range to high-end over long distance. These are the results of local processing, and as we can see, number of threads also plays an important role. The more threads we use to conduct the operation, the more energy efficient we get up to a certain point, but it usually levels off. One thing we can see from here is that Redis is very bad with workload E, as you can see, it's very high. That's in general in all experiments, Redis is not very suitable for this type of workload. But for the others, as we increase number of threads, we do gain some benefit. So compared to those, this is energy expenditure for close proximity processing when we do the offloading from our within our university network from a mid-range CPU to high-end CPU. If we flick back and compare, for example, the levels of the vertical axis here is joules per 1,000 of operation, and we can see that in some cases, for example, for workload D, the values are around 2, and here around 5 or 4. So we do gain some benefits when we offload, but if we take a different look for a particular workload, this is for mid-range CPU, which compares the local execution versus offloading. And as we can see, it does make sense to offload. In some cases, for example, for Redis, it would only make sense if we go to a higher number of threads. But for other databases, even a low number of threads, it does make sense. So if we offload from this weak CPU to a powerful CPU, we do gain a bit of energy. However, when we do the same offloading from high-end CPU, the picture is completely different. We'll see later why this is so, but essentially what happens is we consume more energy when we try to offload from the powerful CPU. So literally, regardless of number of threads, the only gain we can have is with MongoDB high number of threads, but for the others, it doesn't make sense in any configuration. If we take a look closely into consumption of energy of mid-range and high-end CPU, we can notice these blue and green lines indicate the minimum energy that CPU spends and the maximum, meaning that for the green line, we didn't do anything. We stopped all non-essential system services and just waited and tried to see how much the CPU consumes when it doesn't do anything. And for the blue line, we tried to fully load the CPU with some stress testing with multiple computational tasks, and that was the maximum. So what we see here, that for mid-range CPU, the maximum that it does consume, around 15 watts, is pretty close to what high-end CPU does when it does nothing, which was around 10 watts. Which means sometimes we can maybe achieve a better result doing the computations locally, because the actual transmission of data, waiting till data is processed and sending it back, for high-end CPU is very expensive. Even just waiting takes a lot of time. And one other thing that we see here is that databases fluctuate between those two values and rarely reach the top one, meaning they cannot fully saturate the given CPU. That is probably explained by the actual input and output they conduct on the disk subsystem. But anyway, there is still a potential to increase and optimize to fully utilize the available CPU energy. So in conclusion, I'd like to mention a few points we learned throughout these experiments. So Redis is very intolerant to high latency, and not only in terms of performance, but in terms of failures. What we observed is at 50 millisecond distance, it started behaving very erratic. We got many failures, and it's not very suitable for these ranges. Also, we noticed, as I've shown on the graphs, for workload, Redis is very unsuitable and doesn't provide good result. So to summarize, we can see that this data offloading makes sense only under two conditions. So firstly is that the local CPU must be really weak and the remote CPU must be really powerful. And this only works under very low network latencies. Another thing we noticed is that RAPL readings are provided in a CPU register which overflows over time. So it's a monotonous increasing counter that gets overflown on a powerful CPU that's done in around 20 minutes. So we had to take into account this because otherwise if you don't do this, you get negative values. Also, this thing I mentioned about full CPU utilization. And lastly, we also conducted a quick test to see whether network transmission itself and compression and encryption do have any impact on this. So we try to enable and disable, just copy files over and see. But this was very negligible, was only around 2% of total energy expenditure. Lastly, I'd like to point into a few of future work directions that we will conduct in this area. So namely, we would like to repeat the test on different CPU architectures, AMD and ARM architectures. Then we would also like to see how other components of the system spend the energy. So this includes RAM and disk, because for data storage, that would be maybe even different types of disks, mechanical SSDs, or maybe for resource constrained Raspberry Pis, we also are looking into running on SD cards as well. And also, we would like to measure rest of the system, which means on a physical power meter rather than individual components. Also, we would like to see if considering other operating systems would make any difference. This was done under Ubuntu server, but perhaps some OS-specific configuration tweaking might improve our readings. And lastly, for each database, there are numerous parameters that we can tweak, caching, how they store the data, and so on. This would be also interesting to see if tweaking a particular database allows us to achieve better results. So that's it from me, and I'll be happy to answer any questions.
Hello everyone, I'm Artur. Uh, we with Vladimir Sarkan performed analyzed two multiprocessor queuing systems. And our first paper is about computational approach for evaluating steady-state probabilities of multiprocessor systems with waiting time restrictions. This paper is about multiprocessor queuing systems, and in recent years, distributed and parallel computing has increasingly reached this sphere, and it is very important to handle very optimal use of multiprocessor system resources. And in this context, we analyzed the multiprocessor queuing system consists with M processors. Each have a task queue that capacity is N, and in our system we investigate tasks that described by 4 parameters. The first parameter is the number of computational resources that are required to perform that tasks. Second parameter is the maximum wait time that is required to complete that task. And the third parameter is the permissible waiting time that tasks can wait in the queue before before accept to run. And third parameter is the time interval after which the task is allowed to start its service. This parameter in our paper, our analysis, we give to them their value, and we focused on this paper only the fact that our system tasks will have waiting time restrictions. For that parameters, we investigate the distribution functions such as A, B, and W. For more detailed, we consider system states that all system states that from that state our system can pass the system LEG to the probability that system one can be in the state LEG. We denote it PG, and considered all possible system transitions because of the finite numbers of our processor number and the number of Q. The system goes into stable operations mode. That is the state, steady state, and we construct a system of equations and introduce that limitations on the distribution functions. And due to these distributions, we make a system of equations. Our system consists from A matrix that represents the coefficients of parameter of the unknown probabilities PG, and B is the value of combinations of PG. And we designed a numerical algorithm to solve that system of equations. To implement that algorithm, I use a programming language Python and use tools from a NumPy library to optimal solving of that system of equations. Our second work is about the testing of that numerical algorithm, and here I choose any values of our parameters of queuing system, and for these parameters I make calculations. Here are presented some of the values of system steady state probabilities, and using that values of steady state probabilities, we make any calculations. The first is task access rejection probability at any point of time. For this formula and for our based on our calculations, I calculate the task access rejection probability. Also, I make a calculation for task failure probability, and for our example, it has such a value. The third paper that we presented, that is about virtual waiting time in multiprocessor queuing system. Here are the definition of virtual waiting time, but here are very important to understand why we need to analyze virtual waiting time in multiprocessor systems. In classical multiprocessor queuing systems, there are a task queue and a scheduler and computation, the model of computational resources. We investigate virtual waiting time to change this classical scheme to this. Here we introduced a new module. That module is called preprocessor. Preprocessor is what is the software computational algorithmic module that will give a recommendation to the scheduler for optimal servicing of our queue. If we have a computational system and at any point of time arrives task to that system, before its access to the queue, our preprocessor will compute the expected waiting time that it will wait before being serviced. For this, the main goal is to design such a preprocessor to have insight in the sphere of optimal using of computational resources. In conclusion, we proposed a computational approach for evaluating steady state probabilities. Then we utilize that steady state probabilities and calculated any useful probabilities. Then using that probabilities, we make a model to estimate expected virtual waiting time in multiprocessor queuing system. Thank you for your attention.
There is another problem with this stuff, because if you split a large task on a job and send job after job, then it's not enough to have a computation research. You get we're trying to take data from another project, and we know experiments that a lot of people do about here. The difference that this stuff is really big is much higher than using for the computation. So if we are not doing what today we will count the patterns.
Thank you. I agree with you. Thank you.
Based, thank you. Based on this, and here where the big data concept comes from. So in order to be able to deal with all these challenges, a big data concept is generated, which is defined based on 5 V's. So the 4 V's of the big data define the data itself. First one is the volume, which refers to the scale of the data. Next is the variety, which refers to the different types and forms of data. Next is the velocity, which defines the speed that the data is generated from different sources, and the veracity. Here is where the data quality issues rise, and this aspect is what I am researching on. And all these 4 V's have effect on the 5th V, which is the value of the data. This refers like what we can do with that data as we collect them. We need to visualize them, analyze, and make some decisions on them. So this is all refers as value that we can extract from the data. So my research started from data repositories. Mainly, there are 2 types of data repositories where the data is stored on. First one is the data warehouse. Here, the data is stored in a structured way. So in order to store the data in the data warehouses, we need to process the data, clean the data, and make it structured before we load it into the storage. However, in the context of big data, the data warehouse doesn't correspond to the needs, as when processing the data before the loading it into the storage may affect on losing the data and having like just part of the data that we need to work with. So this is why the data lakes have been generated through these past years, which are different types of data repositories that allows the data to be stored in their original format without cleaning it, without doing any processing. And here is how that process goes. So the original raw data from different sources is being injected into the storage, and this process can be referred as a copying process. So we copy the data as it is in its original format, type, volume, and we just store it in a data lake. So after the storage, now we can do analysis on the data. However, before doing the analysis, we need to do some pre-processing process. So cleaning a part of the data that is going to be participated in the analysis, and then do the visualization and analysis on it. In each layer of this process, there are benefits and there are also challenges. So the benefit of injection process is that we have no data loss. All the data is being stored. However, because of the huge amount of data, we need some complex programs and costly programs to be able to provide this process. In a processing stage, the good thing is that we use the traditional processing approaches, and the data is divided into some smaller parts, which are called data marts, to be analyzed later. However, again, because of the volume of the data, the complex programs are needed and costly ones. And also during this processing process, because we kind of take the data and process it for the further analysis, we may have some duplicate value with the storage data, or we may have some missing values that will not be able to participate for the analysis. The good thing for the analysis that data lakes provides is that the new generated data can directly participate in the analysis. However, these quality issues may arise biases in our analysis results, and the decision-making process will be not appropriate. So the data quality problem is like in each stage of this process, and it's being very challenging to deal with this problem. My main problem is to define this data quality problem. Even though there are lots of programs that provides all this process and like provide the entire package of data lakes like the Amazon systems, but these programs are costly and not all businesses can afford integrating this program into their businesses. So my problem is the data quality in all stages of data lakes. And because in the literature, the quality itself has been defined, researched, and lots of dimensions have been established. However, there were no complex solution that will provide something very affordable for the low-level businesses. So my solution is three steps, like consists of 3 steps. For the first step, I need to identify all the quality dimensions that may be good for the appropriate analysis, define the metrics, establish the measurement methods, formulas that will help to compute the level of data quality. Next is to describe the solution itself, the alert system. The system alerts about the quality problems to the user who is doing the analysis on the not pre-processed data, because the organization cannot afford that. And the user needs to know about the quality level of the data that is being analyzed. Also, if the user decides to continue the analysis on that, let's call it a poor data, the user should know the possible biases of the analysis result. So our next stage, the third stage, is about identifying these biases, what can, how this quality issue can affect on the analysis result and the decision-making process. So first step, it was to identify quality metrics, and we have researched the literature and just make a complete quality dimension table with their formulas of how to calculate each one. I will just list the dimensions that we have considered. The consistency is about the data information to be the same, even if the data comes from different sources. Accuracy is how the information corresponds to the real world. Time-related metrics are data freshness and the time that it takes the data to be retrieved from the storage. The completeness dimension is about, it excludes the null values in the data set and checks whether the appropriate amount of data participates in the analysis. Next is the data to be understandable, data to not to have duplicate values, data source to be trustworthy, and finally the user-centric dimensions, which measure how the user is satisfied with the data and if the analysis serves its purpose, if the decision was done good. So next stage was defining the alert system. We defined the alert system that should be integrated in the data lake and prevents the pre-processing of the data before the analysis. So based on the suggested system, when the user performed the analysis, the system itself identifies the quality dimensions that are relevant for that specific analysis, checks on that dimension level, alerts the user about the possible biases, and the user then decides if he or she needs to continue the analysis or needs to process the data for that quality dimension. We defined a quality metric that will help the alert system to work within all this concept, and also the part that analysis result biases should be measured is still being processed by our team. So the quality model is something like this. So it starts from user who performs an analysis, and then the system identifies the quality question which is relevant for that analysis. Based on that quality question, the system decides about the quality dimensions. based on the dimensions, it understands the metrics that should be measured, measures the metrics, and in case of predefined level being low, it alerts about the poor quality. So we have considered a use case about Armenia border crossing procedures. An end user who is a business analyst wants to analyze the export regulatory documentation to be able to make some decision about the border crossing procedures, conducts a query about export level, let's say in 2018. And because we assume that because all programs are costly, the organization doesn't provide the specialists the programs to pre-process the data. So the analysis is done on the poor data. This is what will happen. So the query one is about the export level in 2018. The user will not understand if the answer is based on the poor quality data or good quality data. So he will just take it into the consideration, the answer, and based on that answer, the user will conduct the second query. And as the query goes, the third one, fourth one, and so on, the user will not know about the biases of data quality. And so each next query will be not relevant and not appropriate. After all, the user will spend lots of time on querying, analyzing the data, however, making a bad decision on the data, which may be crucial for the import and export regulatory procedures. Instead of this, if the business decides to integrate the alert system into their repository, after the query one, the user will be notified about the quality dimension issues, and then he or she will make decision whether to continue and have a 5% biased analysis, or to check and only clean the data based on the, in this case, duplicate values. So this will help the user just to understand, maybe he or she is okay with the 5% margin of error, and he or she will just continue without data pre-processing and not spend any time on it. Or he will just spend time on cleansing the data only for one quality dimension and not doing all that complex cleaning procedures beforehand. So this was the use case for Armenia regulatory in border crossing documents, but this alert system may be used in almost all aspects where the big data is imported in. So here I have listed some of them, but wherever the big data is there, we can just integrate the alert system and give opportunity to the businesses who have not enough resources to work with the complex programs and arranged with high-level specialists, but just use the alert system to be sure about their analysis result. So in the end, this is the summary of what will happen. So a user who is just a business analyst or just a data worker will just be notified about the quality issues and then decide what small procedure to apply or not to apply for the corresponding analysis. Thank you. This was my solution. The alert integration of alert system, because we have not completely developed the software. I cannot answer this question as we didn't measure the cost. However, even if it is costly to integrate it, it will be a one-time cost, and doesn't matter on how much data is being updated every year or like per minute or what. It's an it is supposed not to be too slower because my I have also a metric which is time related metric, so it is also supposed to measure the time that it takes to work with that dimension, and it is supposed not to be too tiny.
And the result of this discussion is to tell you, there are four types of data. For each type of data, it is determined the data quality in seven ways. There is a tendency to increase. This area actually states that it's impossible to integrate all the data into manual activity. My question after that, my question is can you estimate what type of data is suitable for the distribution between if you make trials, if you make experiments, certain that if you study very quickly, if you can all the
Thank you. So when I say data quality, I didn't define what it is. Thank you. I will just add it into the talk. But in the model, we let me find that. So we consider the context. It's the context the analysis is being on, which considers like within a specific context, there are specific types of data. So it considers only the dimensions that are relevant for that type of the data. So we here we have the context. I just maybe I didn't include it in my I didn't include it in the quality model, but yes, we consider the context, and based on the context, we define the only dimensions that are relevant for that type of data. Yep. Yeah, thank you.
Hello. I'm Agit Atashan, Senior Software Engineer and Junior Research Engineer at Institute of Information and Automation Problem of National Science. Today I will talk about our team's job about related cloud-based self-organizing UAV swarm simulation platform. Let me introduce what we have done before starting our this topic. Right now, before this cloud-based self-organizing system, we have done a lot of parts of these systems based locally to avoid remote control from user sites from drone side from drones, for example, and we have doing some experiments on quadrocopters. You can see the examples. In this example, we have 3 quadrocopters which doing surveying on some particular points of the area, and one of them can be attacker drone. Just on that one, you can see the peanut cola bank. It will push them in middle of the video. Now, there are a lot of algorithms such now you can see the part of attacking. One of drones doing surveying in some particular point and get the signal about determination particular point which need to be attacked. And it was going out from the swarm and going to that point, then pushing the attacking that point and turning back to their position to continue the surveying process. Now you can see the surveying process continuation and drones going to the landing in their position, where they start the working. And the end of video, you can see the drone which will continue working after landing the next 2 drones. This is the attacker drone, which was going out from the swarm to attack the position. Because of that, his working time being such a longer. Due to this work has been done, developed such a lot of algorithms, such a rotor router model algorithms, and they be adopted to the fixing these problems related with drones. Plus, rotor router with rotor router has been done gossip broadcast algorithms and some algorithms to make security systems to for data transmission. Now, the problems what we have and what we need to solve. Everything before this we was done manually. We should determine the points which need to be survived all manually from such a, for example, from Google Maps or another map systems. And also we need to have a particular distance to be able to join the drones and send the exploration start commands to them to start surveying the particular area. And what our team purposed for this solution, initially should need to be developed a cloud-based server, a client-server application, which should contain all of those developed algorithms and methodologies which had been adopted for this self-organizing system and UAV swarm control. Build a multi-user platform which should support multi-client and multi-server area to be able change the simulation parameters from independently from other users. Build the remote control, remote task sending system, because right now, before this our solution, we should stay together with drone in the same area to join with them with locally shared Wi-Fi and send the tasks or task starts exploration command, and integrate all of these methodologies into a single platform, which will make it cheaper and easily for use. Now, the entire application flow represented here. Right now, we are using the TCP connections and dividing the application parts help us to solve a kind of problem such a distance with staying with drone. Now you can connect to these drones or UAV swarm system independent from your area. You can be, for example, in USA and send the exploration tasks to the drone in Armenia, or I don't know, in every point of the Earth. Plus, we have divided the processing parts, algorithm processing parts, and now it is independent and stays in our TCP-based server. You can see our cloud infrastructure. It's we can have a lot of servers in a single cloud node. Every server contains its own algorithm ecosystem, plus which had been adopted for solving these problems. Plus, we have image processing tool called Open Drone Map. It is open source software, open source and free software, which has been used to combine the images which had been shooted during the surviving process. After shooting images, UAV inside of UAV swarm, we are calling gossip broadcast algorithms, which transfers the data between drones and then sending to the server to have up-to-date data every time. We use such a lot of algorithms to connect with the server and upload some particular areas images. Let me introduce the user sites. This is our client's user interface. We have logging area where we are logging the commands which have been done by user. Plus, we have the particular area image loading functionality to load the image. In this example, we have load image from, we type this image from Google search. Then we need to include add the real coordinates of this image. I mean left top and right bottom coordinates. Then based on special algorithm, we will map every pixel in this image to the real coordinates. Then based on that, automatically the points for surviving will be automatically detected by our software, and the real coordinates will go into the server and will be saved for all of users. Then we have command user functionality to call some particular commands, such as clearing cycles inside of that particular grid, which will be done by user, and generate drone data for drone for traversing by that points and doing survivation process. Then we have the exploration sending commands, changing drone status, making it attacking. If we have some particular information about the positions of enemy, we can just give the real coordinates and drone will start attacking, or just putting that coordinates in our view, it will automatically will be determined and will be sent it. And to make users friendly our application, we have give some count of type of grids which can be used by user to make it easy their work. I mean, let me explain in real example. Now, this is one of I have took a screenshot from our real processing when we start doing simulations. We have the real coordinates, we have the images from Google Map, and now we are just putting the real coordinates of left top and right bottom of this image, and then starting create observation points. These points need to be observed, and when our drones going to in a swarm going to survey these points, they will took a photos and send them to the to each other and to our server. It is necessary to mention what is the corner and border nodes to help our algorithm be more smarter and avoid a lot of steps. It is also one of big enhancements. Then we have marked point P0 as a drone start position, and then send the exploration command to the drone. Now let's say what will happen when we say send this exploration command to the drone. Oh, sorry. It's not necessarily all. Okay. During the exploration, between the points which we have given for surviving, every time drone will took particular photos and then send to our cloud infrastructure. Then in cloud, they will be automatically merged using this Open Drone Map tool with their Python APIs, especially. Then after after drone has been done their exploration, it will go to the back their position, and we have add some functionality to return back the launch point. And now you can see the trajectory of this drone, which has been traversed by the exploration points which we have give. This image has been extracted from another tool, used another utility called Mission Planner. We can track our drone steps, and as you can see, there are all points which you have mentioned has been traversed, and now we know our drone job tasks has been completed, and this is all. Waiting for your questions. Thank you.
That's okay.
So, ladies and gentlemen, thank you. First of all, thank you, dear chairman, to shift presentation because it's not very convenient for us to present it at evening. First of all, I'd like to thank all organizers that they invited us from Belarus. So it's a great honor to be with us today and these days our joint work actually, so which I'll present here, is concerning data cubes. Well, today was already discussed the data lake, but we'll still on the step of data cubes, and together with director of the institution, this institution, Fracha Satyan, I would like also to thank him. We performed a project which is currently coming to the end. And under this project, we performed some steps toward to analyze climate, to analyze pollution. And my presentation here is about evaluation of air pollution of NO2 over Armenia and Belarus using data cubes infrastructures in Armenia and in Belarus as well. And yes, this slide is actually, so this smoke is smoke coming from shuttle Endeavour, and I think it's also a good picture which represents a pollution, because emission of NO2 really big, and it's a really big disaster actually for the whole planet. As for the my first words, air pollution is growing worldwide, affecting public health and environment, of course, and it fluctuates because of climate, because of meteorological situations, because of wind and so on. And there are primary and secondary sources of NO2 emissions, let's say NOx, because not only NO2 but other substances. And let's say primarily NO2 it is a result of burning fuels in utility industry boilers, as well as automobiles and trucks, and also car exhaust, coal plants, power plants, oil metal processing. Globally, actually, so around 40% of total NO2 emission come from human activities, and of course it influences badly to our health. It's not only lung diseases like lung cancer, but also Alzheimer's disease and arthrosis and so on. That's why we need to think about how to prevent this disaster, and how to analyze data which actually may come not only from C2 data, C2 sensors, but for example, not always possibly to obtain data from ground sensors. It also comes from space, and that's why we explore Earth from space. Of course, it provides a lot of data, reliable monitoring of information about physical, chemical, biological systems of planet, and it is called Earth observation or remote sensing technologies. And now we're coming to orchestration of this data, and we need to think how to combine all of this data, which is brings from C2, bring from C2 data and from space together. And that is actually the goal of our work. I will come to this slide later, and we'll say about what is now written in gray. But as for space data, you see here on the slide a very fancy, nice picture, which is actually Sentinel-5P. It is a satellite from a family mission of Sentinels, and it is a joint initiative from between United Kingdom, the Netherlands, and ESA. And actually, so there was a very and brilliant instrument which gives not only data for let's say for other purposes, but also for checking NO2 from space. And this instrument called Tropomi, and it monitors trace gases and aerosols, which is relevant for air quality and climate, and also for ozone, for formaldehydes, nitrogen oxides, methane, and carbon. So currently, we are interested in NO2, and we'll use this instrument. Okay. Yes. So we're saying about that is quite complex task, and data. There are plenty of data, and we need to build the instrument which will bring together all of this data on the one infrastructure, and then to give ability to science and education to use this data. And that's why we are coming to online analytical processing, which is OLAP. And well, it's not a secret, and probably you know that currently there are 5 Copernicus data and information services which are based on the DIAS, called Data and Information Access Services. And well, some of them are quite free, but other commercials. But anyway, even those which are free, unfortunately, we're not able to use it because we're from Belarus, but together with our Armenian colleagues, it is possible to bring this data also for our scientific purposes. And well, here I will just not stop too much about data cubes. Well, it's a great idea for clouds. It's a way to analyze the big data when all data will combining together like a pie, and pointing to the one point, to the one coordinate point. If we have all of this data transformed correctly, we can obtain all of this data, all of the information, let's say data mining for the one region. And of course, it is used for science education. Well, which of course there is a Google Earth engine, which is also possible to say that is a data cube. And as for our colleagues, they have Armenian data cube, which is a very powerful actually infrastructure combining high-speed network software algorithms for different proposals and for NO2 calculations, storage resources, and data processing. And with the help of this infrastructure, we built our Belarusian data cube, which combines also technologies called Open Data Cube and Jupyter. And we're storing data from our Belarusian satellite called BKA, and meteorological satellites informations. Well, different ones, there are plenty. Well, it's also possible because this infrastructure connected to our service called Meteor Eye. You may just browse it and find it very powerful because it gives ability to download data from all over the Europe, including Armenia, even in Armenia, which concerning meteorological data from satellites. And in the future, we hope to include data from our new satellite called RBK, Russian Belarusian satellite, but currently it's just a pilot technical project. Of course, it's not in hardware, but the resolution of this instrument will be like 0.7 meter. Well, it's really powerful. So there's a scheme how we are using this data and writing algorithms. So, yes, bring to science and education services to analyze this data and have their own algorithms by scripts writing on Jupyter platform. So these are currently we have 16 spectral range plus composites data for Belarus, which cover converted to one unified coordinate system, imported automated import of data from Belarusian space remote sensing system and Meteor Eye, and of course database plus file storage. Currently, we're analyzing visible range for fire detection, for night illumination, for cloud types, for density of night fog and dust concentration in the atmosphere. So, and currently, so what we did at the end of the project, this joint project, we put data from the instrument Tropomi of Sentinel-5P and analyze it in sense of NO2 by statistical methods like statistical apparatus, root mean square error, mean absolute error, correlations, coefficients of determination, and we tried to analyze what the situation in Armenia, in Yerevan, and in Belarus, in Minsk. And here we have so here you can see a slide which give correlation between what was obtained in situ by sensors, by ground sensors. It was obtained by instrument Tropomi from the space. It looks very highly correlated, and it's about more than 0.7. So it means that we can rely on this data, and we can rely on this data and to analyze further for monitor the situation over Armenia and Belarus. And you see here that the average surface NO2 level of over Armenia for last 12 months was like this, 0.25 and 10 mole per meter per square meter. And the maximum value of NO2 for the same period was observed in Yerevan. It is 0.65, but actually it's really higher than in Minsk. In Minsk, we have 0.24. Well, you're welcome to Minsk because it's a green and nice, clean city. Now you see here, so we proved that it's really so. Yeah, and as the fancy thing, finally, I would like to show you how we provide these instruments to students. So using our Belarusian data cube, they last year it was a hackathon in Minsk, and our students just did an instrument which was able to show on the map different types of different layers. One of this layer, it is dust pollution and sun pollution. Well, not sun pollution, but illumination, because they actually, so the idea of that hackathon was to build a system which will help to astronomers to observe sky. And of course, it shouldn't be with light. So they showed places where the sky was deeply dark. So that was an instrument. So that was actually, so I think that finally under the project we did a good job and provided instruments not only for temperature and cloud analysis, but also for NO2, like an example. Well, to conclude my presentation, I would like to say three things. Well, ground data and space data are very highly correlated. So please, it's really good to analyze a surface by by space instruments coming from space. Is the first one. The second one, well, it's the same actually. So words like a slogan, which is on my T-shirt. Well, terraforming is not terrifying, but vice versa is very bad. So please, let's do not make our Earth to Mars. Do not convert. And the third thing is, well, it's not very polite, not very formal English, but I think it's the slogan of the conferences connected to science. So only science will help us. Thank you. Thank you.